We are going to see that proper maps, closed embeddings, and diffeomorphisms define open subsets of the set of CR maps between two fixed differentiable manifolds, always considering the strong topology. Indeed, in the last two cases, namely the case of closed embeddings and the case of diffeomorphisms, we are going to see that the openness of these two subsets is a consequence of previous results. The set of CR proper maps is also open in the set of CR maps for the strong topology. This proof is not very difficult and you can do it as an exercise. Okay. Now let us consider closed embeddings. Our next step is proving that closed embeddings define also an open set in the set of CR maps. So an embedding is closed by definition if the image is a closed subset of N. And this happens if and only if the embedding is proper map. So let us prove this result, okay? So F is an embedding, right? And we want to show that F is closed if and only if F is proper. Right, let's see this. First of all, let's prove the implication from left to right. Consider a compact subset of N. Right? What we want to show is that the preimage of N is also compact. Okay? We just want to check out the definition of proper map, right? So in order to show that this preimage is indeed compact, it suffices to prove that every sequence in such a set has a convergence subsequent to some point in that set. Okay? So it suffices to prove that any sequence xn in the preimage of K has a subsequence, okay, x sub n sub k, converging to some point still in the preimage of K. Okay, such that the limit when K goes to infinity, okay, of this sequence over here is some alpha that belongs to the preimage of K. Let's see if we can show that. Right? So what we have, okay, is that the xn belongs to the preimage of K. So the sequence of the image of the xn for every n is a sequence of points in K. But K is obviously a compact set. So there exists a subsequence that converge to some point. There exists a subsequence such that the limit when K tends to infinity of the image of x sub n sub k is some point beta in n. Okay. The issue here is that all these points belong to the image of M. And so beta belongs to the closure of the image. But our hypothesis is that F is a closed embedding. So in particular, by definition, the image is closed. So that implies that beta is equal to the image of alpha for some alpha in M. Right? Moreover, all these points belong to K. Okay? By construction, because all the X n belong to the preimage of K. And a sequence of points in K that converge converts to a point in K. So this guy over here belongs to K. And so alpha belongs to M, but it also belongs to the preimage of K. All right? And so since the limit when K goes to infinity of f applied to x sub n sub k is equal to f of alpha, and f is an embedding, so it's a homeomorphism from M to its image, then we deduce that the limit when k goes to infinity of x sub n sub k is indeed alpha, and alpha belongs to the preimage of K. So we prove that every sequence in the preimage of K has a subsequence that converge to a point in the preimage of K. So the preimage of K is compact. Okay. Now let's see the other implication, which is that if F is a proper embedding, then the image of M is closed, right? So consider a point Y that belongs to the closure of the image, right? And our goal is proving that it belongs to the image, right? This implies that there exists a sequence, let's say xn in M, such that the limit when n goes to infinity of the image of xn is indeed equal to y, right? Because y is a point in the closure of the image. Now, let us consider a compact neighborhood of y. That makes sense because we want to use at some point that f is proper. Okay. So since it's a neighborhood of y, that implies that f applied to xn is a point in K for every n big enough. Okay, that is true. And so, in particular, we get that xn belongs to the preimage of K for every n big enough. But now we can use that f is proper, so the preimage of K is compact, is also compact. Okay, so we have xn that belongs to the preimage of K for every n big enough, and this implies that there exists a subsequence of xn such that the subsequence converge, okay, to a point alpha that belongs also to the preimage of K. We're using that the preimage of K is compact, right? And now what we get is that Y was the limit when n goes to infinity of the image of xn, okay? But obviously, this is also true if we consider a subsequence, right? And now, since the limit of the x sub n sub k is alpha and f is continuous, this is the image of alpha. And in particular, we get that y belongs to the image of m. But that proves that the image of m is closed because we consider a point that was in the closure of the image and we prove that it is in the image. So in particular, the image of m is closed, and so we get that every closed embedding is a proper embedding. Very good. In particular, this simple result that we proved implies that the set of closed embeddings is open for the strong topology, because we get that closed embeddings are, of course, embeddings that are proper maps. But the set of embeddings is open, and the set of proper maps is also open, and the intersection of two open sets is also open. So the set of closed embeddings is also open, right? Or if you prefer, the set of proper embeddings, because it's the same set. We can consider also diffeomorphisms. So it is not a rule, as in the previous case, to try to decompose what a diffeomorphism is in terms of properties that we already considered. And so what we want to see is that a diffeomorphism is an embedding, which is also a submersion and a proper map. All right? It is clear that a diffeomorphism is an embedding that is a submersion and also a proper map. So the inclusion that is not trivial is indeed this one, showing that a map that is an embedding plus a submersion plus a proper map is a diffeomorphism. And we are going to proceed, as we did in lecture 15, to prove that diffeomorphisms are stable. In particular, if you review that proof, we can suppose, by using the same argument, that M and N are indeed connected. Okay? Or a very similar argument. We can suppose that they are connected. And what happens then is that if we consider F that is an embedding plus a submersion plus a proper map, okay, the first thing that we proved there, once we reduce our situation to the case where the manifolds are connected, is that the image of M is open. This is also true here because it is true for every submersion. Okay, and indeed, in that proof, we use that F is a submersion. Okay, then we proved that the image of M is also a closed set. And in there, the argument was a little bit different because in there, M was compact. The image of a compact set is compact and every compact set is closed. So that was the proof in there. But now we can use that F is a proper embedding and proper embeddings are closed. So in particular, okay, we get this result because F is a proper embedding. So since M is connected and the image by a diffeomorphism of a connected topological space is also connected, since M is connected, we have that F is surjective, right? And now we have the following. Since F is an embedding and a submersion, it's indeed an immersion and a submersion. So we have that F is a local diffeomorphism. But it is a local diffeomorphism that is injective and surjective. So it's a diffeomorphism. Okay? And so the set of diffeomorphism coincides with the set of maps that are embeddings, submersions, and also proper maps. And of course, let's write this again. So embeddings plus submersion plus proper. And of course, all these properties to the right define open sets. So the set of diffeomorphisms is the intersection of these three sets, the sets of embeddings intersected with the set of submersions, intersected with the set of proper maps, and the intersections of three open sets is still an open set. So the set of CR diffeomorphisms from M to N is open in the set of CR maps from M to N for this strong topology. In the last few lectures, we studied stability properties in the set of CR maps between two fixed differentiable manifolds. More precisely, we determined several subsets of the set of CR maps that are open for the strong topology. Stability is a very important topic because whenever we have a stable property and a map that satisfies the property, we have that every small perturbation of such a map still satisfies the property. But we are also interested in properties defined in the set of differentiable maps that define dense subsets. And why is that? Because in that case, if we have any map of the set of differentiable maps, we can consider a small perturbation as small as we want, such that the perturbed map satisfies the property that we are studying. And that is really interesting. In order to show that certain properties in the set of CR maps are dense, we are going to need to develop new techniques that we are going to introduce in next lecture. And in particular, we are going to introduce convolution in the next lecture. Thank you for your attention.